Welcome to Spring LIB.
Hi everyone, so what we have here is a problem dealing with rotation and in Second's law. So what we have is a man of weight 150 pounds leaning on a cushion, and that entire cushion is rotating about the z-axis at a speed of 30 feet per second, and the distance from the z-axis to the man is 8 feet. The cushion is at an angle theta, and we know that the coefficient of static friction between the man and the cushion is 0.5. So what we're asked to solve for is the minimum angle at which, or the smallest angle at which, the man would start to slip off. And the way we're going to be doing this is by using free body diagrams, Newton's second law, and by using our knowledge of normal and tangential motion. So what we're going to do first is draw a free body diagram of the man. So the man I'm just going to represent with a box. We have a weight force acting in the negative z direction, and we have a normal force acting at an angle theta. That's our angle theta. And we also have our static friction force that I'm just going to call Fs. Now, by doing Newton's second law in the normal direction, we see that we have forces in the normal direction that are coming from the normal force and the friction force. So what we can do is we can see that this is going to be equal to Fs cos theta plus n sine theta, and that's equal to mv squared over rho. We know that Fs is just 0.5 times n, so this will give us 0.5 n cos theta plus n sine theta, which is equal to mv squared over rho. Next, what we can also do is do Newton's second law in the y direction, the z direction. So we can say that the net force in the b direction is equal to 0 because the man is not accelerating in the z direction. And the only two forces we have three forces acting in the z direction, and that's the weight force acting in the negative z, so that's going to be negative w, or not negative w, just w plus n cos theta minus the static friction force sine theta, and that's equal to 0. We know that the static friction force is equal to 0.5 times n, so we can say that this is w plus n cos theta minus 0.5 n sine theta, and that's equal to 0. So what we can do is we can solve for our normal force here and say that n is equal to w, which as we know is 150 pounds, all over cos theta minus 0.5 sine theta. Next, what we can do is we can go ahead and plug this normal force that we have here, the expression we have, into our normal acceleration equation. So what we can do is we see that this will be equal to 0.5 cos theta plus sine theta times 150 all over cos theta minus 0.5 sine theta, which is equal to mv squared over r. And this gives us 150 over 32.2, 30 squared over r, which is 8. And we can go ahead and isolate this for theta, and what we see is that we get a theta equal to 47.5 degrees. And this is our minimum theta value.